Okay. All right, whenever you're ready. Welcome to SCP-2, I guess. So this single quote by Alexander Polyakov, the man himself, sort of says what this course is about. We are trying to understand many different things from sort of the same point of view. If I may use some more poetic liberty, I might even say that a pot of boiling water is a tabletop simulation of the quantum vacuum. So by the end of the course, probably all of us would appreciate, at least roughly speaking, what that means. So the goal of this set of lectures is, for me, is to understand clearly the question, what is a field theory? If you go and read Nobel Prize lecture by Ken Wilson, he was essentially asking this question during his PhD years and throughout his career, and then he later understood, well, how to understand what a field theory, at least. Of course, this is not a simple question to answer, and most cases we don't even have a clear-cut answer. But from the work of Wilson, what we have is a perspective on how to approach this question, or in general, how to understand what is the structure of field theory. And that perspective is called Renormalization Group. RG for short. RG would tell us how to characterize a field theory and what a field theory does when we vary its parameters in a more concrete way, other than the usual Feynman diagram pictures that we have learned in quantum field theory classes before. Feynman diagrams only tell you so much. If you went to Zaki's talk today, they are trying to understand quantum vacuum in a non-perturbative way. How do you actually approach that problem? This is the answer. How do you understand boiling water? Again, this is the answer. And Dima might be interested in this sort of population dynamics, that this RG idea, philosophically speaking, might help you even think about this problem in a clear way. Not necessarily to solve it, but think about it, at least. So to kickstart this lecture series, let's start with some experimental facts of life. So what we do first is take a magnet, its north and south pole, and just start heating it up. What a magnet means is that it has what's called a magnetic moment on average. When you start heating it up, the molecules inside the magnet that points in some direction, because it's a magnet, all the magnetic moments are aligned in some way. When you heat it up, they start vibrating. And as you heat it up more and more, you imagine things start jiggling randomly, and you end up with zero magnetization. So we essentially expect that if you plot magnetization as a function of temperature, you start with some finite magnetization, zero temperature, and as you go to infinity in temperature, heat it up more and more and more, the magnetization essentially goes to zero. But if you go and do the experiment, this is what you see. The magnetization indeed decreases, but it doesn't asymptote to zero as t goes to infinity. Instead, it just goes to zero abruptly at some finite value of t. And then after that, it just stays zero. This finite value of t we call the critical temperature. So there is one immediate surprise here, that is Usually in physics, things go smoothly. But here, something drastic is happening, something non-smooth is happening at TC. What people have done is go close to the critical point and measure stuff. I don't really know how people measure this stuff, but if you measure the magnetization and how it behaves close to the critical point, we find that it behaves in a particular manner. 0.32. It goes to 0 at the critical temperature with this particular, exponent of T minus Tc.
So that's just below the critical temperature or just above the critical temperature? Yeah, just below, I guess.
Yeah, it is below the critical, right? And you can also measure other stuff like susceptibility. That is, at the critical temperature, you apply external magnetic field. This is proportional to that. You can measure that around here too. That goes like T minus Tc to the negative 1.2. Well, I'm just plopping down these numbers now, and there's another thing maybe you can measure. Go to critical temperature exactly, and then vary the magnetic field and see how magnetization changes with magnetic field, external applied magnetic field. This turns out to behave like this, some number. What's interesting is that I just said magnet. What are the chemical components of the magnet? And shouldn't these numbers depend on the chemical composition of the magnet? It turns out that for any anisotropic magnet, which means there is a fixed special direction on space for the arrangement of the molecules, these numbers are the same, no matter which molecule type is there inside a magnet. So there are two surprises.
The critical temperatures would be different. Right?
Yeah, the temperature at which this thing happens would be different, but these numbers are exactly the same. Meaning at the critical temperature, all of them behave qualitatively and quantitatively the same way. The details differ. TC is different, things like that. So there are two surprises. Surprise one, non-smooth at TC. Surprise two, exponents are same for all anisotropic magnets. This itself is some interesting fact that begs some explanation. But let's go on a little bit further. Oh, by the way, this part, the magnet will be called a ferromagnet. We know this, I guess. This is a paramagnet. Just names. Okay, now we come to the code by Polyakov. We take water in a pot, closed pot. At these numbers I have to remember. At some pressure, about approximately 22 megapascal. Don't ask me what it means. And about temperature, 370 degrees Celsius. Then, okay, any question?
Celsius?
Yeah, come on, it's experimental.
Yeah, it is experimental. I don't know what it is in camera.
It's not a unit, so you can't write T equals to that.
Sure. Right. So what you would see is basically at this sort of values, you would have water below and vapor above. Why? Because of gravity, density is higher for water, it comes down and so on. And it has an average density of about 322 kilogram per meter cube.
That's the water density.
Really?
No, sorry.
This is the average density of both vapor and water. Okay, now yeah, go.
I'm just trying to understand these numbers.
This numbers means nothing. So I just wanted to give a concrete example. So now we just do exactly the same thing, just start heating up. And what we expect is not what happens. We plot the density as a function of temperature. And let's say this is the critical density, which is that. Below, at really low temperatures, we have both these things existing. So people plot it like this. And as we increase temperature, what happens is we end up with a uniform fluid with this density. So it behaves like this at some critical temperature. Oh, this curve looks somewhat similar to that. Now people have actually looked at details.
So the TC is not 370.
No, TC is 374
C.
Okay.
degrees Celsius.
So okay. So I'm a little. So this row C,
Mhm.
you're saying if I took a sealed vessel and I know the pressure is 22 megapascals and the temperature is 370, then that's what the average density of the water and vapor will be.
Yeah.
And then I heat it up, and I reach the critical point. So in other words, if I had a vessel that was at 21 megapascals
Mhm.
and 370 degrees C, then it would have a different density, average density. It wouldn't be 322.
Yeah.
So then if I heat that up,
So
what is my problem?
you wouldn't have this abrupt ending. So you'll get to that in a future lecture when we actually discuss this in some more qualitative detail.
So the pressure has to be greater than or equal to.
Pressure that has to be equal to that.
Oh,
Cannot be less than, cannot be greater than. Just like here, the external magnetic field has to be equal to 0. Cannot be greater than 0, cannot be less than 0. So the critical point is basically TC and B equal to 0. Here the critical point is TC and PC.
Okay. So there's this the phase diagram of water. Is that the triple point or something?
Yeah, it is the triple point. Yeah. But I'm just configuring it such that these things look the same. So here we have a TC and B critical, which is just 0. But here we have TC and P critical, which is not 0.
And the two lines because you're plotting both the.
Yeah. Higher density is liquid. This is vapor.
So row B and row C after TC is not special or anything by construction because you're in a sealed vessel, so you can't change.
Yeah, you cannot change the density. Yeah. Right. So
For the system, can there be only one critical point, or
there can be many, but I'm just, for illustration purposes, I'm just using one. Simple cases that you can actually do experiments. So in the notes that I will send, there is an experiment that sort of does this. You can see this for carbon dioxide, I think.
more than one critical point?
No, just exactly it's the same thing.
So I think for a single system, can there be more than one critical point?
Yeah. It's not prohibited. by anything.
Trying to understand it, but maybe we get it.
These are just motivational examples. So, right. So the point I'm trying to make is, maybe I need a different color. Near the critical point, these plots almost look the same. People went on and they did the experiment. What they did is find rho minus rho c, how it behaves near the critical point. And they found it to be t minus tc to the power some number, right? It turns out to be 0.32.
Wow, of course.
Of course. Now you go ahead and measure something called compressibility, which is proportional to the rho by the external pressure fixed at temperature Tc. And that turns out to behave at T minus Tc. Minus 1.2. Wow. Awesome. Now you go and measure rho minus rho c at Tc. How it behaves as P minus Pc. No awards for this. It's 1 by 4.8.
This is for water?
This is for water. You can pick any molecule, liquid, vapor system, water, carbon dioxide, your shoes or something, just doesn't matter. These numbers are the same.
Do you know if they did the water experiment first and then the magnet, or the magnet?
Yeah, that I don't know. That I actually don't know. So, all right. And there's even more fun things for the TC, at the TC point. What happens is that you get to somewhere in between, right? A uniform fluid and a separated, phase separated, well, vapor water separated system. Something in between. What happens is that inside this vessel you will get a fluid, a liquid like thing, and then bubbles inside it with arbitrary size and shape. And inside those bubbles you would get droplets of water with arbitrary size and shape. And inside that droplet of water you will get bubbles of size and shape. So essentially you would have, stuff like this. This is, let's say, fluid, and something inside, something here. See what I'm saying? You zoom in, and it looks exactly the same. But sadly, you cannot see it for the liquid vapor transition, because since you have bubbles of any size, essentially light can scatter, visible light can scatter, because there are things that is roughly of the order of magnitude as the wavelength of the light. So it just becomes like a cloudy, murky fluid. And that phenomena is called critical opalescence. There are videos of this on YouTube too. And probably this is how they measure these things. I don't know, actually.
So in this setup, you can't change the pressure and temperature independently, though. Because you fixed the density.
Yeah, so here when I change the pressure, I fixed temperature.
But you need like a different apparatus to do something like that, right?
That's probably true. I have no idea, actually. Yeah.
Yeah.
So however you may measure compressibility, which I don't know how, the apparatus is just for visualization aid.
Wait, so why can't you?
Because
So
you fixed the average density at rho c,
Yep.
322. So the pressure is just a function of temperature. It's
Right.
not an independent thing. I can raise the temperature and my pressure will respond to that. So I can't, for example, if I'm at TC, like in that last line, I can't increase or decrease the pressure without either removing or adding material, or squeezing the vessel and changing the shape.
Yep.
In either case, I'm changing the density.
Right.
So that it wouldn't be as critical.
Yeah. But somehow people have measured this. I don't know how. And that's essentially what it does, right? So at critical opalescence, how do you say this word? However you say this word, what happens is that a sort of scale invariance, meaning you have fluctuations in densities, higher density versus lower density at all length scales. No matter which length scale you are, meaning how much you zoom in or how much you zoom out, the system essentially looks statistically the same, right? This is not the same if you are below or above. If you are, say, below and then increase the pressure a little bit so that the density, the favored density is that of a liquid, then you would have bubbles of air inside. But if you zoom out, you will not be able to see them because the bubbles will have a characteristic scale. We'll see all of this in detail at some point, but now just these are experimental facts of life, right? The same is true for a magnet, but I don't know how you would see it other than in a simulation. People have done simulations of a magnet, and at TC, I don't know how they do the simulations. Maybe Gary knows already. At TC, you can see this scale invariance. You zoom in and the magnet looks the same, meaning how they simulate, I guess, is consider a square lattice or something and put spins. And at TC, what happens is that you will have a cluster of up spins inside which a cluster of down spins and so on at all length scales, basically. Fluctuations of average spin, local average spin at all length scales. So the behavior qualitatively and quantitatively are the same for all magnets, all anisotropic magnets, and all liquid vapor. These details obviously would differ, but these numbers stay the same. So why? What's going on? How do we even begin to understand? So the ideas of how we would even understand this mainly come from two people. Well, many people, but for a good sort of storytelling, let's make it two people. Idea number one, I'm not deriving it from anywhere, I'm just stating it. Idea number one comes from none other than Landau, that nature is organized by symmetry. What the sentence or slogan means is that when something happens at some particular value of external parameters, what happens is that, at least this is what Landau realized, that the symmetry, some symmetry of this magnet system in this region got changed to some other symmetry in this region, and they are not of the same type of symmetry. And that's why you have some violence going on here. And what Landau realized is that these system and this system essentially have the same type of change in symmetry. Details to come in future lectures. The second idea is mainly due to Wilson and I think Kadanoff is that nature is organized by scale. This is again some sort of takeaway from this experiment. So these experiments are telling us that near this critical point, the microscopic details of the system do not matter. No matter what the underlying system is, these numbers are the same. So the microscopics cannot depend these numbers. So near the critical point, if you're looking at a macroscopic system, what the microscopics are irrelevant. That's probably how Wilson or Kadanoff got inspired with this idea. They decided to organize the theory that tries to describe this or that phenomena by scale. By doing that, they were able to capture these properties essentially. Putting together these ideas into one framework is the Renormalization Group, as you might have guessed already. So this is what we are yet to see. So before winding up today, I've only prepared so much today. Let's define some things so that future discussions can be less poetic, actually. So defining phases. So how do we understand, or even try to begin to understand any of these systems? We have to do StatMech. There's no other way. So we will work in the canonical ensemble, where the probability for a configuration of the microscopic states is given by e to the minus beta c by z, where z is the partition function, sum over all possible configurations, beta h c, where h is the energy, Hamiltonian or whatever, for the system under consideration. We usually define the free energy as the logarithm of the partition function. And this, in turn, will be dependent on the parameters that goes into the Hamiltonian, and of course temperature and external magnetic field or external pressure or whatever, these external knobs that we can turn. So these parameters of H, I'm going to collectively call it as G and name them couplings. So F is a function of all the couplings, GIs. F of GI is, of course, a function.
And temperature.
And temperature, yes. Yeah. And other stuff like magnetic field and whatever. So the things that we want to compute, like this difference in density for critical density, or compressibility, or even heat capacity, all of them can be cast into a derivative of the free energy. For example, the heat capacity per volume is something like T d2f by dt2. You don't have to remember any of this. We will use all of this in a very natural way when we come to actually use it. But my point is that things can be cast as derivatives of the free energy with respect to some external parameter or a coupling. So what we already have seen is that at Tc, there is some non-smooth sort of behavior. So if we were to compute, the heat capacity, this will also have some non-smooth behavior. That in turn should mean that at critical point, F should have a non-analytic behavior. Its derivative has to be discontinuous or non-smooth, something like that. You shouldn't be able to Taylor expand f at the critical point. Anywhere else, it seems to be fine. So we will conjecture that f is singular at the critical points only. Not necessarily singular, non-analytic at least, right? But that itself is slightly troubling in the sense that, how do you compute f? Through a sum. And h itself we'll choose that to be analytic. So e to the beta h is analytic. A sum is analytic. So how can a derivative or f be non-analytic?
It's a log of Z, right?
Still,
Still.
yeah. The answer is it's non-analytic only in what's called a thermodynamic limit. So a thermodynamic limit just means that we take the volume of the system to be infinite. If, when we take the volume of the system to be infinite, this is finite, then we would say that thermodynamic limit exists. And it turns out from experience with thermodynamics that we know that this is an extensive quantity, so it has to scale with the volume of the system and so on. So this is something that we expect, but not always true. In fact, one of the homework problems is asking you to find the thermodynamic limit, show that the thermodynamic limit do not exist for a system of only positive charges, which is very simple to see. Right. So under this volume going to infinity, the number of configurations a system can have also goes to infinity. That means that this sum becomes an infinite sum. Then this is not guaranteed to be non-singular. That's what's going on. In reality, we have like 10 to the 23 particles. So it's almost infinite number of particles or infinite volume systems. So what we actually expect is, something like this. It's smoothed there if you look close enough, but with 10 to the 23 particles or large enough system sizes, you can never resolve this. For all practical purposes, is in the thermodynamic limit and hence shows singular behavior.
I didn't get that point. So partition function is analytic, right?
Yeah. If without this,
the element that you are summing is analytic,
mm-hmm.
right? When you take derivative, that you take derivative on each of the terms, right? But f is log of
z.
Yeah. Then the log factor comes into play.
Right.
It's not just
Log of sums.
the log of sums. That when you take derivative, you can't take derivative of individual elements.
Yeah.
Otherwise, even in thermodynamic limit, it will still be analytic.
The partition function itself.
Or any derivative of function.
The non-analyticity comes from the fact that you're doing an infinite sum.
Yeah.
No, not a finite sum.
Yeah.
Even in okay, so infinite sum of finite quantities can be
Non-analytic.
The sum converges, I guess.
Yeah, of course. That's too much math for physics, I guess.
Was the thermodynamic limit
sort
of like...
Yeah, it is the convergence, right? In some sense. We are demanding that this exists. If this doesn't exist, we leave we do another problem.
Right.
Yeah.
But I think this question was even if you don't take that limit, um, f itself should still be analytic.
Without taking the limit?
Yeah.
Yeah, without taking the limit, it is analytic.
Oh, I see. Okay.
When taking the infinite volume limit, it becomes non-analytic because of this infinite sum.
I see.
Yeah, I don't know the math super details of why infinite sum should give is guaranteed to give a non-analyticity. I don't think it's guaranteed to give a non-analyticity. Yeah.
You turn the sum into an integral somehow because you're going to this infinite volume.
Yeah. Even though, even after taking the infinite volume limit, the non-analyticities should only appear in at one point in the parameter space. Yeah. So. Yeah. So it's non-trivial, but we can infer this from experiments and do physics from that, right? I guess.
Functions which are non-analytic everywhere are pretty hard to write down. I can't think of any. Have like a nice formula.
Yeah.
You know.
Right. So the idea is that if you look at the space of all couplings, let's say G1 and G2, there is some region where this is non-analytic, the free energy. Let me just draw it like this. If it separates two regions of the coupling space, we will call these two separate regions phase 1 and phase 2 or something. This is another phase. That's just a definition. If in the coupling space there is a non-analyticity like there, then there are no phases for this system.
Because it doesn't cut through the whole.
Yeah, it doesn't separate two things. So it turns out, which we will see later, that for this liquid vapor sort of thing, we have a parameter space, one characterized by something that we'll call lambda. All of this is to come later. And another one, let me just write as G2 and G1. It turns out that there is a non-analyticity along this line, and it separates two phases. And the phases are called, less than Tc will be called an ordered phase, because in the case of a magnet, less than Tc, you had magnet individual moments aligning, giving a total average magnetization. And above Tc, you have randomly aligned things, which is called a disordered phase. So this we will see later. Okay, that's.
Well, in the phase diagram for water, it ends at some point at the critical temperature, right?
Right, but this is not a plot of temperature versus.
So what is this plot of?
These are the couplings of the free Hamiltonian. I haven't discussed what they are, but this is roughly speaking the mass term, and this is the lambda phi 4 term for a scalar field theory.
So you can choose the coupling as you want for the system. I thought the coupling would be fixed for the system.
Yeah, the coupling in general would be dependent on the microscopic details, and some of the couplings will necessarily depend on these external parameters, right? If I vary the temperature, something has to change. What what changes under the variation of temperature, that is still to figure out. We will figure that out in the next to next lecture. And you vary the magnetic field, something has to change. And so these are not the temperature and the magnetic field themselves. These are the parameters that goes into the Hamiltonian, which we still haven't written down.
When we know that how the free energy will change, like how free energy depends on these parameters that we don't know what these parameters are.
Yeah, so the thing is, we don't even know what this Hamiltonian is. So in the next lecture, we'll discuss a very powerful trick of finding this Hamiltonian, which is guessing. So, and guess is based on symmetries and experimental details. And then from that, we will deduce how the parameters of the Hamiltonian would depend on external conditions. That's something I'll try to explain. This is just a teaser. Let's take it like that.
Once you guess the Hamiltonian, then you can determine how the free energy varies as a function of these.
Yes. Yes.
Why do we have to guess the Hamiltonian and not just write it? Like I can write the Hamiltonian, but then I want to do the magnet.
Yeah, but even that, I would argue, is an effective theory because of universality, which I think I defined, right? At this critical temperature, many vastly different microscopic systems behave exactly the same way, right? So to describe all of liquid vapor transition and all of anisotropic paramagnet ferromagnet transition, you just have to find one simple model, because at the critical temperature, everything behaves the same. So we have to find just one simple model, which at the critical point behaves like this. So Ising model is one such model. In fact, I'll not deal with Ising model, I think. I will just deal with the field theory version.
I mean, the choice of Hamiltonian, right, is the choice of the microscopic model. Is that right? No.
It's a choice of the effective model. Microscopic or macroscopic, well, it depends on which scale you're dealing with, which length scale or energy scale.
We have the scale of the microscale, right?
Yeah, like what I'm saying is, if I define the Ising model as a toy model, I would say it's a toy model.
Yeah.
And you don't have to guess at the Hamiltonian. You just write it down.
Right, which is basically guessing. That's what I mean by guessing. You just write it down.
No, but you're not. You're just you're proposing it. You're not. It's not a guess for something else. It's just an example. It's a chosen.
Yeah,
example.
that's what I'm saying. So how do I know ahead of time that the Ising model is going to describe this critical point? You don't, right? So what I'm going to do in the next lecture is to directly try to infer what the long distance macroscopic sort of effective model is based on RG, which what RG is, it's going to be next lecture. RG will give us a set of rules that we can use to deduce which parameters should we keep in a Hamiltonian or effective action, as we will call it, and which parameters are important that we should, not important that we can throw away. And from the parameters that turn out to be what's known as relevant, we will decide how these parameters should depend on external temperature and magnetic field And for that, I'm going to use experimental clues. So this is a slightly different take maybe, but yeah. I could also just say that this is the action, and let's discuss the.
Well, I think maybe effective action is different from the Hamiltonian.
Yeah.
And that's where my confusion is. Because you don't, like, if you have the Ising model, you're not guessing the Hamiltonian. You're just, that is the Hamiltonian of the model by definition. So
Yeah, that's like a definition sort of thing that you're saying. Yeah. So
that's what we mean by, I guess,
yeah, let's think of it like this. You have an anisotropic magnet. How would you describe it microscopically? Okay, let me try this Hamiltonian, which seems reasonable, right? That's the guess part I'm saying. Yeah. So this microscopic part I will bypass maybe in the next lecture or the next to next lecture, and go directly to the effective model, because we want to do field theory and then get to quark confinement or whatever. Yeah. So the take I will follow is Polchinski's paper on effective field theories and the Fermi liquid theory.
So when it comes to the two different phases of water, I still do not understand. Like if I have water, and I put it in a vessel with average density at 300 kilograms per meter cubed rather than 322, and then I start at absolute zero and I increase it to 1,000 degrees, right? Where in this do I cross from the ordered phase to the disordered phase?
Yeah, very good question. Yeah, you have to be somehow at this critical density. So otherwise, if you're not at the critical density, I don't think there is a sharp phase transition.
Okay.
So critical point is a function of temperature, pressure, and flow.
Yeah, but this is fixed in some sense, so it's a function of these two.
Then it seems like there should be only
One of them.
one phase really of water in some sense. Maybe in an artificial restricted sense, there are two phases.
Yeah, this is very restricted in the sense that that's fixed, and so the point is to draw this analogy and see these numbers are the same.
What I was trying to say was, you have like the critical point is that PC, PC, and rho c, right?
Mm-hmm.
So it's sort of a parameter of three variables.
Yeah.
So if you have, I don't know how you can do that, but if you set the temperature to PC and vary PC and rho c, then also can you arrive at this criticality?
Yeah, we are doing it that roughly here. You fix the temperature and see how rho varies as you vary the pressure.
And through the renormalization group, can you say that whether a system can have this criticality or not? Or is it, because you showed these plots on G1, G2, right? They don't have this phase separation, then there is no non-analytical point for field.
Yeah.
And that is all that's required for criticality.
The non-analyticities will be present here too, in the sense that
Just not divide the.
yeah, but I can go from this phase to this phase by going this way.
So you can avoid the criticality, or you just don't have criticality.
Yeah, you're just avoiding criticality, I would say. There are no two different phases, but there is still a non-analytic behavior, which we could call criticality.
And you can have different phases without any criticality. It's first over first.
Right, which is also something that we would see.
Yeah. So.
Yeah.
But it seems like in the restricted, or in this water, specifically at row C, restricted case, you only have one G, so to speak, which is your temperature. And you have a single point of non-analyticity, and so of course that separates it into two disconnected parts because it's just
Right.
one dimension.
So this extra G I'm talking about is not an external parameter. Turns out to be something that's microscopic, which we have no control over.
Okay.
In very rough terms. Turns out, yeah, we'll see that when it comes to that. So this is the, if you remember this thing, it's the lambda phi 4 term in the scalar field theory, and it has no dependence on the external parameters.
Okay.
So this is the only thing that we can control. And we have to tune T to Tc to arrive at the critical point. When you tune T to Tc, it turns out that this G2 thing goes to 0. These are all things to come. Hold your horses, is there.
I hope you're going to explain how water has Z symmetry. Allegedly.
Yeah, so I think that's very roughly speaking, rho minus rho C is minus rho minus rho C.
Yeah, but
Yeah, that's the alleged Z2 symmetry. Yeah,
it's the alleged Z2 symmetry.
yeah. Yeah, so we will write a field theory for this guy, or interpret the field theories for this guy.
Why is that? I don't see why that should be the case.
Yeah, exactly. That's why we will leave water here and look at the magnet.
No, but we wanna look at water because
That's what Polyakov said, yeah.
Well, do you know what water is made of?
well, does the water actually exist? If I'm not looking, if there aren't humans around.
Well, the water could be made up of strings, and it could exhibit Lagrangian symmetry.
What does not change under that symmetry?
The effective Hamiltonian do not.
Yeah, I think I've seen critical exponents before, but I never understand it. These just seem like random numbers which
Yeah.
have nothing to do with physical constants.
No, they have nothing to do with physical constant. They should be thought of as some fundamental constant, right?
We should not be working with decimals. And they might look better in some other places.
Yeah, so this is a spoiler. So all of this was described for a three-dimensional magnet and a three-dimensional liquid vapor system. When we discuss the effective field theory, it turns out that we cannot calculate this directly, at least. So we have to do some sort of numeric stuff. Even this effective field theory business would fail for 3 dimensions, but 4 dimensions, awesome, we'll do it. 3 dimensions, we'll do some desperate things and find something close to this, but that's not the real way people have found it. Apparently they did numerics. But 2 dimensions is, on the face of it, looks extremely hard, but it turns out to be solvable exactly. And these numbers are, good fractions, like 1/8 and so on. That's because of the magic of 2D conformal field theory, which, if I understand it, by the end of the semester, I'll try to explain.
You can just solve the 2D Ising model with that.
That's also true. Yes, exactly. You have exact solutions. So, yeah. And Yeah. Right.
In one dimension, I have no phase transition.
In one dimension, there is no phase transitions, yeah. Which also we would explain at some point.
So why is 4D suddenly easy?
Which is also something that we should see in the future. It has a good reason under RG. Even without RG, we can describe why it is the case. Anything above 4 dimensions, yeah.
4-dimensional analytic solution of the Ising model.
It's just dimensional analysis.
Yeah, exactly.
Wow.
Exactly. Yeah. Anything above 4 is trivial. Yeah. Yep.
Why did we have to live in 3 dimensions?
Yeah. Okay. That's it for today.